Welcome to today's session. In this video, we'll explore LeetCode problem number 1631, path with minimum effort. This is a fascinating problem that combines graph traversal with optimization techniques to minimize the effort required to traverse a grid. Let's dive in and break it down step by step. In this problem, we're working with an MXN grid called heights, where each cell represents the height of a specific location in a 2D array. The task is to determine the minimum effort required to traverse from the top left corner, at coordinates 0, 0, to the bottom right corner, located at M1, N1. A valid path is defined as a sequence of adjacent cells where you can move in any of the four cardinal directions, up, down, left, or right. Now, the effort of a path is calculated as the maximum absolute difference in heights between two consecutive cells along the path. The goal is to find the path that minimizes this maximum difference and return its effort as an integer. Let's take a look at an example to understand this better. Given the input grid heights equals 122, 382, 535, the output is 2. Here's why: the path 00-01-11-21-22 has a maximum absolute height difference of 2. Breaking this down step by step, moving from 0, 0 to 0, 1 gives a difference of 2, 1 equals 1, then from 0, 1 to 1, 1 gives 8, 2 equals 6, followed by 1, 1 to 2, 1 with a 3, 8 equals 5, and finally 2, 1 to 2, 2 with a 5, 3 equals 2. The largest difference in this path is 6, 5, and 2, but among all possible paths, the minimum effort path has a maximum difference of just 2. The key takeaway from this example is that the path's maximum difference, 2, is the smallest possible among all valid paths. Now, let's consider another example. For the grid heights equals 123, 384, 535, the output is 1. This time, the path 00-01-02-12-22 achieves this. As we analyze the differences step by step, 00 to 01 gives 2, 1 equals 1, 01 to 02 gives 3, 2 equals 1, 02 to 12 gives 4, 3 equals 1, and finally 1, 2 to 2 gives 5, 4 equals 1. In this path, the maximum difference is just 1, which is the minimum effort required. To further solidify this, consider the grid heights equals 12111, 12121, 12121, 12121, 11121. Here, the output is 0. The path 00-01-02-44 has a maximum absolute difference of 0 because all adjacent cells along this path have the same height. This means there are no height differences to consider, and the minimum effort is 0. This demonstrates that when all cell heights are equal, the effort is automatically minimized to 0, regardless of the path taken. Finally, let's review the constraints and edge cases. The grid has dimensions MXN, where both M and N range from 1 to 100. Each cell height in heights is between 1 and 10⁻⁶. Some edge cases to consider include: if the grid only contains one cell, the effort is 0 as there are no neighbors. If all cells have identical heights, the effort is also 0 since there are no differences, and for large grids, such as 100x100, the solution must be optimized to handle these efficiently. Additionally, the algorithm must manage large height differences accurately, even when values reach the upper limit of 10⁻⁶, ensuring no overflow or computational inefficiency occurs. When tackling LeetCode problem number 1631, path with minimum effort, the objective is to traverse from the top left corner of a grid to the bottom right corner while minimizing the maximum effort between adjacent cells along the path. Here, the grid can be visualized as a graph where each cell represents a node, and the effort, or absolute height difference between two adjacent cells, serves as the weight of the edge connecting them. One strategy to solve this is the brute force approach. The idea here is to explore all possible paths, calculate the maximum effort for each path, and retain the minimum value among them. While this guarantees correctness, the sheer number of potential paths grows exponentially with the grid size, making this method computationally prohibitive, particularly for larger grids. The time complexity of approximately O for M*N makes it impractical in real-world scenarios, even though it serves as a baseline for understanding the problem's constraints. Another approach to consider is binary search combined with DFS or BFS. This method reformulates the problem as a decision problem. Can we traverse the grid with a maximum effort of k? By using binary search over the range of possible efforts, we can determine the minimum effort required to complete the path. For each candidate value of k, DFS or BFS is used to verify if a valid path exists within the given effort constraint. This strategy is more efficient than brute force, as it reduces the search space significantly. The binary search involves O, log, E, iterations, where E is the maximum possible effort, and each DFS or BFS traversal operates at O, m*n, resulting in a total complexity of O, log, E, *m*n. While this method is more efficient and balances correctness and practicality, implementing and managing the combination of binary search with DFS or BFS adds complexity to the solution, making it more challenging to debug and maintain. A more elegant and efficient solution to this problem is to use a modified version of Dijkstra's algorithm. In this approach, the effort between two adjacent cells is treated as the edge weight, and instead of minimizing the total path weight, as in the traditional Dijkstra's, we aim to minimize the maximum edge weight along the path. A priority queue, or min-heap, is used to prioritize paths with the smallest current maximum effort, ensuring efficient exploration of the grid. To avoid redundant processing, we keep track of visited cells. The time complexity is dominated by the operations on the priority queue, which is O, m*n, log, m*n. This method is both efficient and conceptually straightforward, directly addressing the problem without requiring additional abstractions like binary search, making it a strong candidate for solving the problem. The chosen strategy for solving this problem is Dijkstra's algorithm due to its alignment with the problem requirements and its efficiency. The key insight is recognizing that the problem revolves around minimizing the maximum edge weight in a path, which is naturally handled by a variation of Dijkstra's algorithm. This method not only provides an efficient solution with a time complexity of O, m*n, log, m*n, but also simplifies the implementation compared to alternatives like binary search with DFS or BFS. Although binary search is a valid alternative, it requires multiple grid traversals, roughly log e times, which is less efficient for dense grids. Additionally, combining binary search with DFS or BFS increases code complexity, making Dijkstra's algorithm a more straightforward and practical choice. By directly addressing the problem with a single traversal strategy, Dijkstra's algorithm effectively balances efficiency, correctness, and simplicity. To summarize the trade-offs, the brute force method, while correct, is computationally infeasible due to its exponential complexity. Binary search with DFS or BFS is more efficient but introduces additional layers of complexity, making it harder to implement and debug. Dijkstra's algorithm stands out as the optimal solution, offering an excellent balance between efficiency, correctness, and simplicity. By traversing the grid and minimizing the maximum edge weight along the path, Dijkstra's algorithm efficiently solves the problem while maintaining clarity in implementation. This makes it the most practical and effective strategy for solving path with minimum effort. In the problem path with minimum effort, we are tasked with finding a path from the top left corner of a grid to the bottom right corner, while minimizing the maximum effort required along the way. The effort between two adjacent cells is defined as the absolute difference in their heights. To solve this, we need to balance two key objectives: finding a valid path and ensuring that the maximum effort along that path is as small as possible. We can think of the grid as a graph, where each cell is a node and edges connect to adjacent cells, with the edge weights representing the absolute height differences. To minimize the maximum effort, we can employ binary search. By hypothesizing a maximum effort and verifying if a valid path exists under that constraint, we can systematically narrow down our solution. For validating whether a path exists, we can use techniques like breadth-first search, depth-first search, or union find to check connectivity. This approach is far more efficient than a brute force solution, as it reduces the complexity significantly by leveraging the binary search over the possible effort values. The algorithm begins by pre-computing the range of possible efforts. The maximum possible effort is determined as the difference between the smallest and largest heights in the grid, which helps define the range for our binary search. We then initiate the binary search with low set to 0 and high set to this maximum possible effort. At each step, we calculate the midpoint of the current range, mid equals low plus high, //2, and check if a path exists from the top left corner to the bottom right corner with the maximum effort limited to mid. To validate this, we use a pathfinding function. For example, with BFS, we start from the top left cell and explore its neighbors. We only move to a neighbor if the effort, which is the absolute difference in heights, is less than or equal to mid. If we can reach the bottom right corner under this constraint, the function returns true, otherwise, it returns false. This iterative process helps us zero in on the minimum possible maximum effort. Once we determine whether a path exists for a given mid, we adjust the binary search range accordingly. If a valid path exists, this means we can potentially lower the maximum effort further, so we reduce the search space by setting high equals mid 1. If no valid path exists, we increase the effort threshold by setting low equals mid plus 1. When the binary search concludes, the low pointer will hold the minimum effort required to traverse the grid. To implement this effectively, we utilize some key data structures. A priority queue, such as a min heap, can be useful when employing Dijkstra's algorithm to explore paths with the lowest effort first. A visited set or Boolean grid ensures that we do not revisit cells unnecessarily during BFS or DFS. Alternatively, union find can efficiently handle connectivity checks, especially with optimizations like path compression and union by rank. In terms of complexity, the binary search operates logarithmically over the effort range, while each pathfinding operation is proportional to the grid size. This results in an overall time complexity of O log max underscore possible underscore effort asterisk n asterisk m, where n and m are the grid dimensions. Finally, let's consider some edge cases. For a single cell grid, there is no movement required, so the minimum effort is simply 0. In the case of a flat grid, where all cells have the same height, the absolute difference between any two adjacent cells is also 0, resulting in a minimum effort of 0. For large grids, the algorithm remains efficient due to the binary search optimization. By narrowing down the effort range logarithmically and validating paths in linear time relative to the grid size, the solution scales well even for grids with thousands of cells. These considerations ensure that the algorithm is robust and can handle a wide variety of input scenarios effectively. Here, we start by importing the necessary module, Heap Pop and Heap Push, from the Heap library to manage our priority queue. Next, we define the solution class and the minimum effort path method. The input is a 2D grid of integers called heights, which represents the elevation of each cell. First, we determine the number of rows and columns in the grid and define the possible movement directions, right, down, left, and up. Then, we create a helper function is_valid to ensure that a given coordinate is within the grid boundaries. We initialize a min heap with the starting position, 0, 0, and an initial effort of 0. Alongside this, we create a min_effort grid, where each cell is initialized to infinity, representing the minimum effort required to reach that cell. The starting cell at 0, 0 is set to 0 since no effort is needed to begin. Now, we enter a loop to process the heap. In each iteration, we extract the cell with the smallest effort using heap pop. If we reach the bottom right corner of the grid, we simply return the effort at that point since it signifies the minimum effort path has been found. Next, we iterate over all 4 possible directions to explore the neighboring cells. For each neighbor, we calculate the absolute difference in heights between the current cell and the neighbor, which represents the effort required to move between them. We also compute the maximum effort encountered so far along this path using the max function. If this computed max_effort is less than the current recorded effort for the neighboring cell in the min_effort grid, we update the min_effort value for that cell to the new max_effort. This ensures that we are always storing the minimum effort required to reach each cell. Once updated, we push the neighbor, along with its updated effort, into the heap using heap push, so it can be processed in subsequent iterations. This loop continues until we either find the minimum effort path to the bottom right corner of the grid or exhaust all possible cells. Finally, we include a return-1 statement at the end of the method, though it is effectively a safeguard that should never be reached since the problem guarantees a valid path exists from the top left to the bottom right corner. This implementation ensures that we efficiently calculate the path with the minimum effort using a priority queue, optimizing the process with a time complexity roughly proportional to O, n log n, where n is the number of cells in the grid. Here, we start with the Java implementation for solving the path with minimum effort problem. First, we import the necessary packages and define our solution class with the minimum effort path method. The input to this method is a 2D array representing the terrain heights. We determine the number of rows and columns in the grid and define a directions array to represent the 4 possible movements: right, down, left, and up. Next, we initialize a priority queue, heap, to store our traversal states, where each state consists of the current effort, x-coordinate, and y-coordinate. The queue is sorted by effort in ascending order to ensure we always process the least effort path first. We also create a min-effort array to track the minimum effort required to reach each cell, initializing all cells to integer.max_value except the starting cell at the top left corner, which is set to 0. The main loop begins by processing each state from the priority queue. We extract the current effort and position, and if we've reached the bottom right corner of the grid, we return the effort as the result. Otherwise, we iterate over the possible directions to explore neighboring cells. For each neighboring cell, we calculate the new coordinates, NX and New York, by applying the direction offsets. We check if the new coordinates are within the grid boundaries. If they are, we compute the effort required to move to the neighboring cell as the absolute difference in height between the current cell and the neighbor. The maximum effort along the path to the neighbor is then determined as the greater of the current effort and the calculated height difference. If this maximum effort is less than the effort previously recorded for the neighboring cell in the min-effort array, we update the cell's effort and add the state to the priority queue. This ensures that only paths with reduced efforts are considered for further exploration. Once all possibilities are exhausted, the loop exits, and we return -1 as a fallback, though this line should never be reached since the problem guarantees a valid path exists. To begin solving the problem, we start with a simple 2x2 grid where the input heights are given as 1, 2, 3, 4. First, we initialize our variables. The number of rows and columns are both 2, and we define the possible directions for movement as up, down, left, and right. We also initialize a heap with a starting state of 0, 0, 0, where the first 0 represents the initial effort, and 0, 0 is the starting cell. Additionally, we maintain a min_effort matrix initialized with infinite values, except for the starting cell which is set to 0. Now, we begin processing the heap. The first value popped is 0, 0, 0, representing the starting cell at 0, 0, with an effort of 0. From here, we explore its neighbors. Moving to 0, 1, the height difference is a 1 to 2, which equals 1. The maximum effort becomes 1, so we update min_effort 0, 1 to 1 and push 1, 0, 1 to the heap. Similarly, moving to 1, 0, the height difference is a 1, 3, which equals 2. The maximum effort is updated to 2, and we update min_effort 1, 0 to 2 while pushing 2, 1, 0 to the heap. This completes the first round of processing. Now let's analyze a larger 3x3 grid with the input heights 1, 10, 6, 7, 14, 2, 3, 5, 12. Again, we initialize the variables. The rows and columns are set to 3, and the directions remain the same. The heap starts with 0, 0, 0, and the min_effort matrix is initialized with infinite values except for the starting cell, which is set to 0. The first cell processed is 0, 0, with an effort of 0. Exploring its neighbors, moving to 0, 1, the height difference is a 1 to 10, which equals 9. The maximum effort becomes 9, so we update min_effort 0, 1 to 9 and push 9, 0, 1 to the heap. 4, 1, 0, the height difference is 1 to 7, which equals 6. The maximum effort updates to 6, so min_effort 1, 0 becomes 6, and we push 6, 1, 0 to the heap. As we continue processing nodes, we always pop the cell with the smallest effort from the heap, update its neighbors, and push valid moves back into the heap. After processing all valid paths, the destination cell, 2, 2, is reached with a minimum effort of 9, which is returned as the result. In this edge case, we analyze a flat grid with all heights equal to 1. Here, the input heights are 1, 1, 1, 1, 1, 1, 1, 1, 1. After initializing the variables, we notice that all height differences between neighboring cells are 0. As we process nodes from the heap, all neighbors will have an effort of 0. This means that every time we push a new cell into the heap, it will always have 0 effort. The heap is updated with 0, x, y for all reachable cells, and the algorithm progresses smoothly across the grid. Finally, the destination cell, 2, 2, is reached with a minimum effort of 0, which is returned as the result. This demonstrates that when there is no variation in heights, the minimum effort will always be 0. In this solution, we use Dijkstra's algorithm with a priority queue, or min-heap, to efficiently determine the path with the minimum effort. Let's analyze the time complexity step by step. First, creating the min_effort matrix, which tracks the minimum effort required to reach each cell, takes O, rows asterisk calls, time, as we initialize it for every cell in the grid. Next, the heap operations dominate the runtime. Each grid cell is pushed into the heap at most once, and the heap can contain up to rows asterisk calls elements in the worst case. For each node, the heap pop operation requires O, log, rows asterisk calls, time, and pushing its neighbors into the heap also costs O, log, rows asterisk calls, for each neighbor. Since there are up to 4 neighbors per cell, this results in a total cost of O, rows asterisk calls, asterisk log, rows asterisk calls, for all heap operations. Finally, processing the neighbors for each node involves checking their validity and calculating the maximum effort, which requires O, rows asterisk calls, time for all cells. Combining these steps, the overall time complexity is dominated by the heap operations, which gives us O, rows asterisk calls, asterisk log, rows asterisk calls. Now let's discuss the space complexity of the solution. The heap, which is a priority queue, stores at most rows asterisk calls nodes, and each node takes O, 1, space. Therefore, the heap requires O, rows asterisk calls, space in total. Additionally, the min_effort matrix, which is used to keep track of the minimum effort required to reach each cell, is also of size rows asterisk calls, contributing another O, rows asterisk calls, to the space complexity. Besides these, there are a few constant space variables, such as the directions array used for neighbor traversal, which takes O, 1, space. When we combine these components, the overall space complexity of the algorithm is O, rows asterisk calls. To better understand the efficiency of this approach, let's compare it to a brute force or naive solution. A naive approach would involve exploring all possible paths from the top left corner to the bottom right corner of the grid. With rows asterisk calls cells, the number of unique paths could grow exponentially, as each cell has up to 4 possible directions to move. This results in a worst-case time complexity of O, for caret, rows asterisk calls, which becomes infeasible for large grids. On the other hand, our optimized solution uses Dijkstra's algorithm to explore only the most promising paths based on the smallest effort. By avoiding redundant calculations and focusing on priority-based exploration, we reduce the time complexity to O, rows asterisk calls, asterisk log, rows asterisk calls, making this approach significantly more efficient and scalable for larger grids. Let's delve into the best, average, and worst-case scenarios for this algorithm. In the best case, when the grid is small or the heights are uniform, meaning all efforts between cells are equal, the algorithm might terminate early after visiting only the starting and ending cells. Here, the heap operations are minimal, requiring O, log, rows asterisk calls, time, and the initialization of the min_effort matrix, which is O, rows asterisk calls, becomes the dominant factor. For the average case, typical grids require processing all cells, and the heap operations dominate, leading to the time complexity of O, rows asterisk calls, asterisk log, rows asterisk calls. Finally, in the worst case, every cell in the grid is processed, and each cell pushes its 4 neighbors into the heap. Even in this scenario, the time complexity remains O, rows asterisk calls, asterisk log, rows asterisk calls, as the logarithmic cost of heap operations continues to dominate. To mathematically justify the time and space complexities, consider the grid with rows asterisk calls cells. Each cell is processed exactly once, and up to 4 neighbors per cell may be pushed into the heap. The cost of each heap operation is O, log, rows asterisk calls, as maintaining the heap's order involves logarithmic time complexity. Therefore, the total cost is proportional to the number of cells multiplied by the logarithmic cost of heap operations, resulting in O, rows asterisk calls, asterisk log, rows asterisk calls. For space complexity, the min_effort matrix requires O, rows asterisk calls, space, as does the heap at its maximum size. Together, these dominate the space usage, giving us an overall space complexity of O rows asterisk calls. One common mistake when implementing Dijkstra's algorithm is neglecting the use of a priority queue. Dijkstra's relies on efficiently extracting the smallest value at each step, and using a simple list instead of a priority queue can drastically increase the time complexity to O open parenthesis n times m close parenthesis squared. To avoid this inefficiency, it's important to use a priority queue, such as Python's Heap, which ensures that the extraction of the minimum value happens in logarithmic time. Another frequent issue arises with the binary search range. Some solutions set the range from 0 to the maximum possible height difference across the entire grid, which can be unnecessarily large. Instead, the upper bound should be the maximum absolute difference between adjacent cells' heights, as this keeps the search space tighter and more efficient. Additionally, when performing binary search, reusing the visited array without resetting it can lead to incorrect results, as paths from previous iterations may remain marked. To address this, the visited array should be reinitialized during each iteration. Finally, a conceptual error occurs when minimizing the sum of absolute differences along a path instead of focusing on minimizing the maximum absolute difference at any step. This distinction is crucial to solving the problem correctly. Edge cases are another area that is often overlooked, but they are critical to consider. For instance, grids with only one cell or grids where all the heights are uniform might behave differently than larger or more variable grids. Testing cases like single-cell grids, uniform height grids, and grids with extreme height differences ensures your solution is robust. Now, regarding interview scenarios, this problem is an excellent opportunity to showcase your understanding of path optimization techniques. It can be tackled using two main approaches: binary search combined with BFS or DFS, and Dijkstra's algorithm. Mastering both methods demonstrates your adaptability in solving graph problems. Many such problems involve minimizing or maximizing certain path metrics, so being comfortable with BFS, DFS, and priority queues is a valuable skill. Each approach has trade-offs. Binary search with BFS or DFS is often simpler to implement and explain but can be slower for large grids due to repeated searches. On the other hand, Dijkstra's algorithm is generally more efficient, though it requires familiarity with priority queues. In interviews, be prepared to explain why Dijkstra's guarantees an optimal path by discussing how it handles weight constraints effectively. There are several related problems that build on similar concepts. For example, LeetCode 743, network delay time, also uses Dijkstra's algorithm to solve a shortest path problem. LeetCode 778, swim in rising water, shares a similar structure and involves binary search with BFS or DFS. LeetCode 1102, path with maximum minimum value, focuses on maximizing the minimum value along a path, offering a different perspective on path optimization. Finally, LeetCode 329, longest increasing path in a matrix, explores pathfinding in a grid using DFS, emphasizing sequential relationships rather than differences. When considering alternative approaches, binary search combined with BFS or DFS works by performing a binary search over the maximum effort value. For each effort level, BFS or DFS checks whether a valid path exists. This approach has a time complexity of O log max_diff *n*m, where max_diff is the maximum absolute height difference, and it is relatively straightforward to implement. However, it may be slower for large grids due to the repeated search process. On the other hand, Dijkstra's algorithm treats the grid as a graph where edges represent absolute height differences. By using a priority queue, it minimizes the maximum effort efficiently with a time complexity of O n*m*log n*m. While Dijkstra's is more efficient, it requires careful implementation to manage the priority queue effectively. Another alternative approach is the use of the union find algorithm to determine connectivity. In this method, all edges, representing height differences, are sorted, and the algorithm progressively connects components in the grid based on the smallest differences. The goal is to determine the minimum effort necessary to connect the top left and bottom right cells. This approach achieves a time complexity of O n*m*log n*m due to the sorting of edges. While union find is highly efficient in scenarios where connectivity is the primary concern, it can be less intuitive in interviews compared to BFS, DFS, or Dijkstra's algorithm. However, understanding this method can provide a valuable alternative for certain cases, showcasing versatility in problem solving. Great work! We've successfully explored the path with minimum effort problem and its solutions. From graph traversal algorithms to optimization techniques, we've covered key concepts that can help you tackle similar challenges in the future. If you enjoyed this video, make sure to like, subscribe, and stay connected for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!